Hi, David.
Hey, Pam, how are you?
Not too bad. How are you?
Very good, very good. So I finished up the master algorithm. It's okay, not bad.
Yeah.
Not too bad. So and what's next on my list, Pam? Tell me. What do I need to read?
I don't know. I have lots of good recommendations. What kind of things are you looking for?
Try me. Do you have anything good on evolutionary programming that you're aware of? I was thinking of trying to tackle the book that you sent me on the renormalization group. I haven't read through that one yet.
Which one was that? I don't remember.
You sent me a very interesting, it's right here. Where is it? I think it's this one. Arrive. Anyway, no, it's a.
But on the evolution, like I think the one I told you before, why greatness cannot be planned by Kenneth Stanley.
Oh yes, I listened to his machine learning thing. Sure,
okay. That's a really good book. I've read it twice. I don't often read nonfiction books twice, but.
Okay, so I'll buy it right now. Sorry, well, we're waiting for the others. So let me get that one on Audible. What's it called?
Let me just make sure. I think it's called Why Greatness Cannot Be Planned. He's come up with some other stuff too that are like recently I think he's working at OpenAI and he came up with some evolutionary, like more technical stuff that's really cool.
They literally, like if you look at the 2-minute papers, they literally just announced doing evolutionary programming at OpenAI. Morning, sir. Yeah. Love the sweater. I can't quite read it, but
it's a question mark and the American flag. I can guess where it's going.
Just looking at your, you're still muted, Rob. We can't hear you. Sorry. You're muted. We can't hear you. Ah, there we go.
Sorry, this was a Costco closeout. I needed a sweatshirt once.
That works too.
It's actually a nice sweatshirt. So, I'm doing yard work.
Cool. Great. They don't have the Audible version, but I'll thank you, Pam. That's very good. No, I was just letting Pam know I finished the master algorithm by Domingos, which is very good.
And you go through those books so fast, it's amazing.
For hours a day listening to audiobooks, I get through them.
You don't watch too many Netflix shows, I guess.
No, I'm not big into fiction of anything. If anything, I just play the occasional computer game. But yes, should we wait for Rose? Let's wait for Rose for a couple of minutes, just see if she can make it. Yeah, so it's interesting. Pam, have you worked with any of the evolutionary programming stuff?
No, I'm really fascinated by them. I really want to get into it, but I never had the occasion. I know it seems like it is a lot of like a big learning curve. It's not like you can just go start. It needs a lot of computation. It seems to need a lot of experience to get it right. And yeah, I never had the time to look into it, but I think it's really, really interesting.
Yeah, so what they do is they take little functions that go from a number to a number, like sine, cos, tan, log, exp, a bunch of those functions that are monoidal. In other words, the output is the same as the input, and I kind of just throw them in a bag. And then they draw out random functions and arrange them in random graphs, and then evolve them, right? So they have some tasks to do. You've got these random functions connected together in some random graph. And then you have some objective, and then you run the graphs, and whichever one's the best one, you take that one and you will take the best two, and then you just mash them together, and then you try that, and you just keep doing this. That's very much the theme of what I wanted to talk about today. So you can essentially evolve these sparse function graphs using just any old functions. You literally just take a bunch of functions and chuck them in a pot and see what comes out, right? It's soup.
I mean, what makes them like super interesting to me is like one of the few places where you're not using gradients to guide your actions, right? So it's completely gradient free, black box. but so it's, I mean, it makes it a lot slower, but I think you can get to solutions that you can't possibly get to by following gradients, because you might just be in a very off space in your search space, and following gradients will just get you to a local minimum. Whereas these evolutionary algorithms, you can basically go anywhere. It's just if you're willing to wait long enough.
Yeah, that's right. Yeah, if you're willing to wait 2 billion years, you get life.
Yeah.
So, yeah, so that's kind of the argument.
I guess my discount rate's a little higher than that.
Yeah, but I'm just saying that, and we can get into it. It looks like Rose isn't coming in, but basically, if you look at the document, I added a new section. I can share my screen. Let me do that. Where is it? Oh, it's vanished. Show windows. Devils in the oh, did you read the devil in the details, by the way, Pine?
I'm partly through it. It's not an easy read, so I'm trying to understand everything I'm reading. So it's a lot of equations and stuff, but I really like it. Yeah, it's really good. It's
Okay,
an unusual book.
I like unusual books. So let me just hang on. Sorry, I screwed up my screen share. Let me try again. Sorry. Oh, okay. So this one. Yeah. So if we go down here, I've got this conceptual progression that we were talking about last time. Let me make it a lot smaller and a lot easier to read. So just bear with me here for a moment. I'll make it small. And let's do this. And that should be, is that reasonably readable? It is.
Yes.
Yeah? Okay.
Thank you.
All right. So what I'm saying is that you have your bucket and then you throw in a function. Well, what is this function that you've thrown in there? Well, it's literally just something that given some concentration of A, it will diminish that population, increase some population of B. So if I have a bunch of numbers, it'll take those numbers and turn them into other numbers. Right. That's all it's doing. And then we have a Markov chain where the output of that feeds into the next function, and you just get a straight linear function, which is basically chains together and they commute. So this gets into category theory. So you can essentially collapse those functions into a single function. This is called a cone in category theory. And you can also do that with a function graph if it only has a single input and a single output. But for every pair of inputs and outputs, you can collapse it to a single function. So these things are essentially convergent. So that's the wrong word. Anyway, let's move on. And so a stable structure is a structure whose simple existence promotes its own continued existence, right? So if you have a stable system, like an economic system that has equilibrium, it will tend to remain stable, right? It has inherent within it, the likelihood is that it will continue to exist, other than just random. So I'm struggling with emergent behavior. I think emergent behavior is the same as marginal probability. I think they're the same concept. So the idea of marginal probability, as I understand it, is the likelihood of something happening excluding all else, right? So you ignore context, you ignore everything, you just say, given this thing, then the likelihood is that, you know, it will generate this or do this or perform some function. And so I'm not trying to say there is a difference between emergent behavior and marginal probability. I'm not saying that, but I just like the term emergent behavior because it kind of resonates better. But to me, they're the same thing. I could be wrong. Okay, now we get into means, which is really complicated. So a self-replicator is different to a emergent property in that if I have a dice and I roll a dice, it has the emergent property of producing sixes, right? So if I roll a dice enough times, I'll get a 6. It'll happen eventually. If I wait long enough, it'll happen, right? So Boltzmann's argument, as I understand it, is if you wait long enough, everything will happen, but you might have to wait a very long time. Is that your understanding, Payam? Is that his fundamental idea?
I guess that's the ergodic principle, right? It's like
Yeah.
for a
I'm just checking my own
random
thinking here.
walk. Yeah.
Yeah, so eventually, randomly, you'll get everywhere. Like there's no reason why you won't get there if you just randomly walk around long enough.
Mm-hmm.
Right. And so really it's just a question of how long you have to wait. So things that have a higher chance of emerging will populate a world far more often than things that won't. So if there is no replication, essentially when you look at the population of a given system, what you're seeing is the things that emerge from that system naturally. So you'll see the output of its emergent behavior. And theoretically, if you come back 1 million years later, you should see roughly the same distribution. Right? There's no evolution happening. It's just a system that has some stochastic properties that generates stuff over time. And if you go back and sample it at any other given time before or after, it'll generate roughly the same thing. Right? If I take a die and I roll it 100 times today or next week or 10 years from now, there's no difference, right? Nothing has changed or can change in the system. So that's all I'm trying to say is that a system that has emergent behavior essentially is stable in that whenever you measure the outputs of that system, they should be roughly the same regardless of what time you sample them. Okay. Is that a reasonable?
Yeah, it's a lot of stuff. I need to think about it.
Yeah, I mean, those are kind of the assumptions underlying classical statistics as well.
Right. But they don't work when you have a self-replicator, right? If I have some topsoil and I leave it there 1,000 years, nothing will happen. If I plant a seed in it and come back 10 years later, there'll be a tree. That's not the same.
But replication and I guess life in general and its stability that goes against sort of equilibrium statistical mechanics, I think that's separate from emergence. I don't think.
I think they are separate, yes.
Yeah, so I totally, yeah, I understand. Yeah, I guess the whole replication and life is about the stability. So I guess it's evolved to be whatever is stable is basically alive and whatever is not stable is not alive, just by definition. So yeah, you're right that maybe we come back whatever, a couple 100 years, some of the life forms will still be very similar to what they are now. So in that sense, they are stable, fighting. They basically, I think Sean Carroll has had an expression that was really good. They're parasitic in the increase in entropy. So the entropy in the universe is increasing and all of us are sort of riding on the wave in a parasitic way, like extracting entropy so then we can preserve ourselves and in some ways even get better for a short time before dying. So I thought that was a really good way of looking at it. But emergence is like totally different, I guess. It's a different animal, I think.
And I'm trying to paint it as such, I believe. Right? I'm not saying that emergence is the same as life. It's not. Mm-hmm. Emergence to me is something very akin to marginal probability. It just means that it's the output of a system. It's not the system producing itself. So a factory, you know, if I build a factory, cars will emerge from it. I don't think that's a mistake to say that.
Yeah, but that might be slightly different than I guess how people define emergence. I think one of the properties of emergence is that you can't predict what's going to emerge. Like fundamentally, is without running the whole simulation forward long enough, there is no way to know.
So there is a distinction between emergence and marginal probability.
Yeah, I don't know what marginal probability is, but I think just based on the words, like I don't think you can put probabilities on it, and that's one of the features that.
So for example, that's the distinction between emergent behavior and entropy. There's a difference between a known unknown or chaos and entropy, which is truly the unknown unknown. I think there is a distinction. Maybe. I don't know. I'm trying to.
Yeah, but I think the emergence is about like new structures that form that didn't necessarily have to form or you couldn't predict. Like if you look at the evolution of the eye, for example, if you go look at the history of the evolution of the eye, the purpose of the eye was not seeing. There was like other things that were happening, and at some point it transitioned to something that you could see with. Before it was for totally different purposes. So there was no sort of direction or plan to develop something like a car that you said that it was planned out. You execute these things, then the animal can see, and then that's good. There was no planning.
Right. So what I'm about to show you is not emergence in your understanding, right? Mm-hmm. So that when we have salt crystals forming. Sorry, I'll just try and get to the bit where they're actually forming here. So this is not emergence to you.
I don't think so.
Okay,
It's just pattern formation, I guess.
interesting. Okay, then I need to look deeper into emergence because I mistook this for emergence.
Yeah, I could be misunderstanding it. I mean, that's just my understanding.
Okay, no, that's fine. That's why I called the meeting today. Okay, cool. Very good. All right. Okay, fair comment. Okay, so there is a distinction here that I missed, and I'll go back and do some more reading on it. Okay, so let's talk about replicators. Okay, so where I'm going with this is, can we build, first of all, a simulation that can exhibit this kind of life or exponential growth? And then if we can build a synthetic data generator, can we build a system that can detect emergent behavior, or let's call it marginal probability, and distinguish marginal probability from exponential growth? So if I have a system that's generating something, let's say it's generating numbers, and those numbers, when I run the system in one mode, they all appear between 0.8 and 0.9, you know, somewhere in there randomly, and they'll keep generating random numbers in that zone. And then something will happen and the numbers will start to get bigger over time. They'll just get bigger and bigger and bigger and bigger. Can we detect that? Can we say that there's a mean or there's a replication system? This is the output of an exponential growth replicator inside the system. I don't know. That's where I'm trying to get to. Can we build a mean detector? Can we build something that can detect, first of all, a stable system that's just sitting there and it's, you know, reasonably stable, and then something evolves in that system that is mimetic and has this ability to self-replicate, and we see the properties. I'm not saying it will be exponential. I think the correct term is sigmoidal, but can we detect it is my question. Can we essentially take patient data and monitor that patient over a period of time, and then in monitoring their data, we see that something about their metabolism has changed, and they've gone from being stable to having some exponential thing happening to them that we should then, you know, diagnose or see if we can understand why it's changing. Does that make sense?
It's detecting it is easy, right? I mean, that's what they do, right? You go do a blood test every few months and they keep looking at whatever number they're looking at and see if it suddenly starts rising, that raises red flags, right? Like it's just a thresholding, right? But I guess finding out what it means is a different animal. I guess I don't know how you would go about figuring that out.
Right. Is that a useful thing to do you think? If we could build a detector that you could give it a data stream and we could detect the emergence of replication in it? I think it would be, but I'm just curious what you think.
But I guess, I don't know, I guess there's a bunch of things I don't know how you're defining. I guess growth doesn't necessarily mean replication. And if it's just growth you want to detect, all you need is a threshold. You don't need an algorithm. You just need a if statement, right?
Okay, so you just set boundary conditions on the finite game, and if it leaves the finite game, then whatever the rules were of the finite game have been broken and violated, and now we're back in the infinite game, and they need to remove the boundaries in order to make the next.
Yeah, I mean, another sort of field that tries to deal with this is phase transitions, right? I mean, you can call it a phase transition. You go from one phase to another. Usually it comes with a discontinuity in some parameter they call order parameter, right? There's some order parameter in some systems. It's easy to define what it is, in others it's not. And then you see a sudden jump in the order parameter and you know something changed.
Okay. I'm happy to drop all this language and use language that already exists. I just don't know what the language is that exists. So that's my kind of challenge here. Is I'm perfectly willing to believe that nothing I'm talking about is even remotely original. I just don't know what it is in another language so that I can use that instead. This is why I was thinking of reading the renormalization group, because I think it covers the phase transition stuff that you're talking about.
Mm-hmm. So,
Go ahead, Rob.
Yeah, if you say if it exceeds a threshold and then it attract your attention, how do you define the thresholds?
Yeah, so I mean, there's no magic answer to that. I was referring to the medical case, right? If you see like your blood test, usually there is like A, B, C, and there's 3 different thresholds. So the first one is pass, you go into the B regime and it say, okay, you need to be careful, like keep monitoring. If you go to C, go see your doctor immediately, something is gone way off. So I think it's just coming from domain knowledge. In terms of the phase transition, I think is maybe the threshold is not necessary because you just look at maybe the derivative, and if there's a sudden change, that tells you something has happened. Like you don't know, we don't care how much the change is, just how fast it was. So there's like a time scale where, or the discontinuity where you suddenly see a jump. But in practice, I mean, I don't think there's any magic answer. You just sort of go with your best guess and domain knowledge.
Yeah, but if you don't have kind of, if we're looking at the developments of these memes or evolutionary behavior, we kind of lack the domain knowledge because almost by definition, they're going to be somewhat unexpected.
Yeah, I mean, so there is a concept of first order phase transition and second order. So first order is a sudden like jump, like almost like a discontinuous, like a meme suddenly becomes a meme overnight, and it just exponentially grows, like maybe even super exponentially grows overnight. And then there's other types of phase transition that are like slowly, continuously changing, and maybe there is no clear threshold, it's just slowly changing. You could come with an arbitrary threshold or just wait. So that would be more like the sigmoid function I think David was talking about, like it grows and then it slows down. Yeah, I don't know.
I mean, that there is a literature looking at what are called control charts, which basically try and establish thresholds. But even within those thresholds, people, if certain patterns are noticed, then that seems to trigger something that's going to happen. But again, all of those are really kind of closely tied to a domain knowledge. And I think that kind of at some point, if we saw some type of emergent behavior and all of a sudden, it was everywhere, Biden and his bicycle challenges or something like that, then we can say that that's relevant. But I wouldn't have been thinking about him riding a bike. So I mean, I'm kind of wondering, how would I have picked that up in the data? I mean, how could I operationalize that?
I just want to draw one more distinction, if I may. No, it's totally very, very good point, Rob. Completely there with you. I just want to kind of make a distinction down here, which I get to. Where is it? I thought I put it in here somewhere. Maybe I didn't. There's a distinction between a it looks like I've lost some text here.
So, Pam, you called that a phase one and or a stage one?
First order and second order, because one of them is a derivative of the, like if you look at the order parameter, one of them is the first derivative, one of them is the second one, or there's a discontinuity in the first derivative or the discontinuity in the second derivative. So one is a smooth, second order phase transition is smooth, first order phase transition is a jump.
I see.
I think you can even take it further, right? Like you can ask, okay, like a Biden and the bicycle, let's say you want to generate a meme, and that's the whole game people try to play in social media. What should you generate to predict that it's going to become a meme, right? Like that's the whole game. That's another level of understanding you need to have. What are features of things that are likely to be memes?
I don't think you can predict that.
But I mean, advertisers try, right?
I know, but I don't think you can predict it, is my point.
Yeah, you can't predict it, but you can probably give yourself a better chance.
You can get its higher statistical likelihood, but prediction is not possible in my opinion.
Yeah, exactly.
Yeah, you can't predict the success of your company. You can't. Right? You can.
But that's different, right? Because that depends on. So
well,
maybe
you
it's
control
the same,
that to some degree.
Yeah. Yeah, a meme probably you have no control over. Maybe you get lucky, somebody really connected notices your meme, posts it on their media, and then suddenly becomes a meme or not, right?
That's right. Yeah.
Well,
And
then,
yeah.
yeah, I mean, if you pay off the right influencers, I bet.
Yeah,
that
that's another way
impacts.
of doing it. Yeah.
But it's not a guarantee. Like it will get out there and you'll get coverage, but it may not be picked up, right? Yeah, so I'm not claiming that they're predictable. I'm not, but I am claiming they're detectable.
But they did try, I don't know what the results of the experiments were. So they tried to train a neural network to generate music that like earworm music, like the kind of music that you just can't get out of your head. They just trained it with a bunch of pieces of music that people find really like they can't get it out of their head, and it generated something. But unfortunately, I don't remember what happened to it. But maybe that's one way to do it. Look at all of the previous memes and try to learn something that they have in common.
That's a social media motif, which is not that interesting to me personally. And like, if you're into social media, fill your boots. I'm more interested in kind of the medical / social aspects of this. So,
Well, granted, but I do think it's a similar problem.
I'm not saying it's a different problem. I just have limited interest in.
So how do you connect? How do you see a connection between the memes and the medical domain?
So I see the body as a complex system. And when you have a complex system and you zoom out a long way, my argument is that you'll start to see functions and function chains and function structures and memes and stuff emerge at a much, much higher level, given some complex system. So given some bucket of soup, you will see functions emerge in that soup. You'll see, chains of functions emerge. You'll see emergent behaviors. You'll see memes. You'll see all sorts of, you might even see agents emerging in the soup.
So what's an example of a meme in a human body? Like I can't even think about.
Cancer.
Okay, so that's something that, that's uncontrollably replicates and messes with the system. Okay,
right.
Fair enough.
Yeah, or you go through a behavioral change that has a negative or positive impact on your metabolism or something, right? So this is the downward causation stuff that you're talking about. So I really took your comment on downward causation very seriously last time. I've been thinking about that a lot. And I think that there is actually, in the same way that I've been thinking about this idea of having a complex system, and if you have a complex system, you look at it at a distance, you start to see functions and so on. I think that your argument is absolutely correct, which is if you see something that is a soup, then there is a way that you can essentially influence the soup remotely, which is the downward causation stuff, where I don't understand the soup. I don't have any, individual control over its elements, but I can still essentially impose, and I don't have good language for this yet. I'm still thinking about it, but I can essentially impose something on that soup, that system, that complex system from a distance that has an effect on it. And I don't know what that is yet. It's not functions, it's not function groups. That's emergent properties from the small to the large. I don't know what it is the other way around.
Yeah, I mean, I was thinking about this stuff a few years ago, and one other, maybe it's sort of too adjacent of a field to this, but it had the right vocabulary for my understanding, was like, if you look at control systems, right, there's a concept called like under-actuated control. So actuated control is you have your whatever robotic arm, your car, you have full control over it, right? You have under-actuated means you have some control, but not on everything. You can sort of push certain knobs, but you don't know anything about the rest of the system. And I thought that was interesting. And they have a whole like body of work of how to control under-actuated systems, which is really, really hard. But I think it might be relevant to what you're trying to do as well.
Is that the Peter Abel, Sergey Levine crowd that was doing that?
This is from like classical control theory, maybe long before Peter Abel, but I mean, Peter Abel is also a control theorist. So yeah, he works with robots, but I'm thinking like more generally in terms of, I was planning to go look at the literature of how they deal with this, how they model these systems and bring it to something other than control.
Okay, I'm interested in that. So let's if you find any references or can find anything, just fire it my way and I'll certainly look into it. That sounds very relevant.
I mean, you can even make it super general, like the way we talk. like me asking you, David, can you please pass me the paper is an under-actuated control, right? I am controlling you to do what I want you to do. You don't have to listen, but language is one example of under-actuated control. Works at long distances. It's not perfect, but you can get people to do what you want by just asking it, right?
Sort of, sometimes.
Yeah.
Okay, so let me write that down before I forget. Under-actuated control. I'll ask Paul Webos about that actually. I'll sign him with that. Or actually, even what's her name? The lady whose video I sent you?
Frederica.
Frederica. Yeah, sorry, I don't have a pen here. Anyway, I'll just type it in the note to myself.
I mean, control is in my mind because so I'm like in my new role at Amy, I'm supposed to come up with a research program. One of the places I wanted to look into was the combination between control and machine learning. And so I reached out to an old professor that I used to work with at SFU, and he works in control systems and physics. So at some point, I'm going to go to the university and see if they do interesting stuff.
Okay,
so
well, can I come?
I think so. I don't know. I'm supposed to possibly give a talk, but they're going to tell me if there's enough interest, or if not, I'm just going to go to that guy and talk to him.
Cue Rob.
Sorry, what?
Oh, you were going to ask Brian to do a talk.
Yeah. I'm good timing. Anyway, yeah, I was wondering if I could get you to talk to my class a little bit. Just, things you think people ought to understand and things you find interesting.
Now you got to narrow it down a little bit for me. You don't want me to show up and talk about chess or something.
Well, I mean, data science, interesting. So if it involves chess, that's fine. If it involves soccer, that's fine. Yeah, saw part of a presentation the other day from Alteryx. They're trying to predict who's going to win the World Cup.
Mm-hmm.
But if we could do that, that'd be really interesting. I mean, you've got a very different orientation, at least, than these guys. And to be honest, I mean, I really get a lot from your comments because, yeah, it's just kind of like emergent.
Yeah. I basically I wing it every time. No, I appreciate it. Though.
Yeah, I mean, that's, we all kind of do that too. But so, the setup, we could either record this up front or we can do it live. The class runs on Thursdays at 6 Eastern time. So that'd be
3 p.m.
3 o'clock your time.
Okay.
I'm doing this. I'm going to do a 10-minute one this coming Thursday if I can. I'll try. I may have a conflict. 3 o'clock.
Okay. What is the class? Can you say?
It's a basic machine learning class. So we're talking about CART models, neural net, nearest neighbors. I do a little bit on reinforcement learning. Little NLP. Basically, what I'm trying to do is to give them a sense of sort of what they can do and how they can do it.
Mm-hmm.
And so most of these people these are evening MBA students, so they're kind of mid-level management.
Mm-hmm.
And I'm just trying to give them kind of a broad enough skill set that they could, one, do something with it, and two, talk with other people in their organization about things that they might want to do.
Mm-hmm. Mm-hmm.
So, I mean, I see this as sort of the kind of the sweet spot in the sort of data analytics world.
Mm-hmm.
It's, we're not spending a lot of time on it. I mean, I show them how the algorithms work and I give them problems and they've got to go solve them. Prediction
Mm-hmm.
problems.
You should get them to read the book Prediction Machines. That's like a go-to book for all managers when they want to get into machine learning. Have you heard of that book?
No, I haven't.
It's been required reading for 2 companies I worked at. And I thought I didn't like it to be required, but then I read it. It was actually pretty interesting.
So what's the name of that book? One more time.
Prediction Machines. So basically, it reframes the whole field of like machine learning as prediction, and then it basically gives reasons for why it's all about prediction and how you get value out of prediction. It's by AJ Agrawal.
I just bought it. Thank you, Pam.
Yeah, so I think for economists, I think this should be a must read. It's
I would
simple,
also
but it's also
recommend
very
the master
insightful.
algorithm if they want to go a bit deeper.
The simple economics of artificial intelligence. Is
Yep.
that it? Okay, good.
On
Thanks.
my list, I'll have that read by next time.
But let me think about that a little bit, Robert, to see if I can.
Yeah, it's just so. I mean, tell them some of the stuff you're going to talk about, David.
Yeah, so where I was going was DALL-E. I don't know if you guys have been playing with DALL-E, but we're obsessed with it in my family. Where I'm going with that is that in the past, when you wanted to create a campaign, you would have to go to the internet and buy assets and they wouldn't be quite right. And then you'd have to get a graphics designer to do something and so on. What I'm saying is that with these very large internet models, you don't actually need to look into the past at all. You can actually look forward. So you can use programs like DALL-E, DALL-E 2, and Imagen to essentially generate new content based on text, and you can tune that text to your desire. And with DALL-E 2, you can actually find the background image that you're looking for and then draw an area in it and say, a guy holding a blah here, and there he is, and you get variation, you pick the one you want. And so in this motif, you don't have to worry about copyright, you don't have to worry about originality, because the machine is generating new content all the time. And so it really changes the game of how you go about creating campaigns and how you go about generating content, because all the copyright stuff and all of the expensive online image stores aren't really necessary anymore. You can actually just use these AIs to generate net new content of your own desire as you wish. And that has a fundamental impact on the way that we structure organizations. Because we would have a bunch of people sitting around, a bunch of very creative, very, very, engaged people sitting around co-creating new material constantly using AI assist, and they would be able to generate campaigns in minutes that would take, hundreds of thousands of dollars and months of planning in previous generations. So that's the kind of tipping point I'm going to talk about.
That sounds pretty interesting. I mean, you can even go beyond images, right? Like NLP, so when I worked at Unbalanced, we would basically get GPT-3 to generate headlines, and they do better than human generated headlines in many cases.
Right, but there's a human in the loop, right? This is very, very much, this isn't some black box cooking data in the background giving you 42. This is, you and a bunch of creatives sitting around a computer screen together and co-creating stuff. It's a very, very different way of approaching.
But it might not continue to be that way, right? Like, I think when so I play a lot of chess, I give you a chess example. So when 1997, the Deep Blue beat Kasparov, so at the time, Kasparov and a bunch of other chess masters could sit, and so Kasparov plus Deep Blue was better than either Kasparov and Deep Blue, which is where we are now with DALL-E and GPT-3. But now an engine is way better than all the humans working with the engine, even, because they would pick the right, any changes they suggest is likely to be the worst outcome. So basically, at some point, the machines took over and they do way better than machine-human collaboration. So that could be the future.
It could be the future. Okay, so I'll put that in as the punchline, but thank you for that. Yeah.
Well, yeah, that and some of your other simulation stuff too.
Okay, sure. I'll throw in some of my other social simulation stuff as well.
Yeah. So, I mean, again, what I'm trying to do is to get these guys to kind of open up their minds to, you've opened a door and entered in a room, and everything is different.
Very different. Very, very different.
I mean, their world's going to be different, and those who can understand that are going to be much more likely to evolve.
Yeah, this gets back to
So yeah, I mean, anything in kind of the RL space, you know, examples of it. You know, I've talked about Atlas, but that's about it. The Boston Dynamics guys.
Oh, they don't actually use any machine learning with it.
no.
Oh, they don't? I thought that was.
It's all classical controls, like very tuned by like amazing experts.
Yeah.
Very difficult.
Ah, okay.
I actually met the guy that doesn't work at Boston, but he's as good as the guys in Boston, because all the guys in Boston don't say anything, but there is a guy at Caltech. I was in one of my previous companies. We looked at all of his walking robots at Caltech, and they're pretty impressive. Yeah, but there's no machine learning, none at all. So,
But to me, that's even more impressive that you can do that complicated without machine, just doing the math. But then imagine what would happen once they bring in machine learning to help out with that. I think that's the exciting part.
Yeah, I mean, I would think those robots would be really sort of operationally fragile.
yeah, currently.
Well, you've seen them being kicked, right? They don't look fragile at least.
Well, no, I mean, in the sense that, you know, you have a robot doing a task. Okay, now maybe you move it another inch, and what's going to happen?
Well, I mean, traditional control, I think, is actually way better than dealing with that than machine learning. Like reinforcement learning would completely fall apart because it's all based on statistical variations that it's seen in the data. So if he hasn't seen it, it's going to mess up. Whereas control algorithms, they're very model based. So if you have a good model of the dynamics of the system, you don't care in which condition you're in. You can control it like extremely efficiently.
Yeah, I could easily see something happening where you're getting sort of out of your comfort zone, and then what happens?
Yeah, so I mean, so that's actually is exactly related to the kind of research I wanted to do. There's a subfield of control called robust control, where you basically get a mathematical guarantee that in the worst possible case, you're going to be stable. So what usually happens is that makes your robot very sluggish, and it gets very, very scared. It doesn't do anything. But then if you bring in machine learning to recognize when it's safe to go outside and be a little bit more adventurous versus be safe, I think that's where you can combine both of them to deal with the problem you just mentioned.
Yes, I mean, to me, this sounds like Federica's dynamic control stuff.
Who is Federica?
I got a link here. I'll send it to you. I'll post it in just a second. Got to find it.
So we interact with some of the greats from the previous generation of AI who are still very much active. And so Paul Werbos, one of his PhD thesis, he reinvented backprop according to some, but yeah, no, he's a very, very smart guy, and he has friends. He ran the National Science Foundation through the rise of AI. So he was instrumental in self-driving cars and numerical control and all that stuff. Like, he's a genius. And Frederica's a genius too. I'm not arguing.
He's a smart guy. Yeah.
And Frederica's a smart lady. Holy schmoly. Yeah.
Is that another meeting you guys have?
Yeah.
Okay.
Yeah, this is one that was set up by my brother, kind of Doug Neal, and kind of loosely called Friends of Doug.
Yes, I've been going to it for what, 15 years now. Must be
a lot less than that.
Very long time. I've been
This
going
is the organization.
Yeah, if you watch the video, you'll get some understanding.
Oh, that looks really cool. That looks like very aligned with the kinds of things.
Oh yes,
yeah,
no, I'm very interested in Frederica's work. We could probably get her onto this call if we ask nicely.
Oh, definitely, yeah.
Very nice lady.
I'm looking for the. Here it is. This is a book she recommended. And they've got a conference coming up in the fall.
Cool. I'll check it out. Dynamic data-driven application systems.
Super smart lady, Pam.
Yeah, and
Whoa.
it's one of these. I mean, that's a great thing I like about hanging out with folks like you is I'm thinking about something, and then someone comes along and says, well, sure, okay, now that problem has been addressed in this area and solved in this area. And it's like, okay, good. I can use that.
I actually make that my first assumption, which is nothing I've ever thought or done is original in any way, and it's served me well. So,
well, some of the applications would be original.
Yeah.
It used to stress me out, when I had what I thought was an amazing idea, I would be stressed to check and see that that's been done. But I mean, if you think about it, if somebody else has already done it, that's great. You can do something else. Like there's enough stuff to do. Like the more stuff people have done, the better. So
Yes.
no, I don't look at it negatively.
No, I don't look at it negatively. Quite frankly, I just look at it as how do I find it, right?
In general, the payoff is not so much in the idea, but in the applications of it.
Unless you're an academic, I guess.
Well, even there, finance, economics, or at least it used to be kind of applied math. Now, economics has gone over the deep end.
Okay, so I just want to and pull us back if that's okay. So Payam, Rob's asked, I'll do this one. You can do another one in the future. Think about it and let him know. So I just want to go back to I don't know whether we should call it marginal probability or whether we should call it emergence. I don't know. But what I'll say is that certain systems have emergent means. In other words, if I leave them there for a while, something will emerge that is a self-replicator, right? It's not a very good one, but like a salt crystal, if you will, it'll create copies of itself using its own existence, right? So I am a machine that makes me. Well, that's the whole idea of the replicator. So when you have a supersaturated solution of salt and you put a salt crystal in, I don't want to call it emergence, we can call it whatever you like, but it does self-replicate, right? Like you can see exponential growth. Those crystals get bigger over time. And that just emerged from the system. At some point, some random thing happened and then the whole thing turned into a crystal. So that's an emergent meme or an emergent replicator that just happens by itself. Like if you wait long enough, it'll happen. But then there's another class, which is like what I call a free floating meme, which doesn't do that. It actually requires the presence of other memes to generate it. So it's a variation on a variation on a variation on a variation, back to an emergent meme. So there was a system that generated salt crystals, and those salt crystals then generated other replicators that generated other replicators that generated other replicators. And you end up, when you go down this stack of replicators, with what I call a free floating replicator, which would never come into existence if you waited a trillion years, right? It's so statistically unlikely to emerge that it's ridiculous. And it is its precondition is other replicators. So there is a difference, right? And I think that cancer is an emergent mean, right? There's a statistical chance that cancer will emerge that is, very low, but not zero. Human beings or David, zero. Like it's never going to happen, right? So can we get machine learning systems to generate free float, what I call a free floating meme? Like, can we essentially create a system where there are emergent memes in it, and those emergent memes generate through replication with variation things that would never emerge, in an early stage, of that system or not.
I don't know if you check this out. I don't know if you have seen these videos. Do you guys know about slime mold?
Yes.
Yeah, this is like a clear example. I shared the video, like a clear example of oh, why is it like that? Of emergent behavior from, but it doesn't like if they actually, you can train slime mold to solve mazes.
That's
right?
just YouTube. Sorry.
Yeah, that's just a YouTube one.
I need the action.
Sorry.
And I can search for the text.
I don't know what I did with it.
I'll just search for the text. Hang on.
Okay, sorry, I just copied it.
Oh, I found it. Yeah. Okay. So I found the video. All right. So it's this one.
So they used to think that there is a queen slime mold that would direct all the slime mold particles or individuals to do what they need to do to find food in the forest. And that was like a predominant theory for like decades. And then there was a group of people who came out, I can't remember her name. There's somebody, some kind of biologist, I guess, or a computer scientist. So they went for a sort of a decentralized system. So basically every slime mold, all it does is just looks around it and decides what to do based on the concentrations and directions and all that. And the collective behavior of looking for food or assembling versus disassembling, it just is an emergent behavior. None of the actual mold entities know anything about any strategies. They don't know anything about what's happening outside. They don't get any information except from their immediate neighbors. And somehow you get this emergent behavior of like looking for food. When it's not there, everybody disperses and there is no mold. And then the next day they collect somewhere else and then they go look for in different directions. If you look at the video, it almost looks like an A-star search. They just learned how to do A-star search. They go in all directions. Maybe not that video, but you can just keep going down the rabbit hole of slime mold videos on YouTube. You see like really amazing behavior.
Yes.
So in this case, I guess I'm trying to understand. So there is no replication, but there's still emergent behavior. Do you call this also a meme, or is that a separate thing?
So the strong claim, which I sometimes hold, is that all we have is dumb machines and memes. That's it. That's all you need. So if I have a bunch of atoms over there and I apply memes to them, they'll organize into some structure that will then organize into some structure, etc. So the strong version of it is that the memes is all you need. So if you have memes and stuff, or if you have a system that can produce memes and stuff, you'll get the world. That's the strong view. There's a weaker view where there's other stuff in the mix, but in the strong view, slime mold is just a bunch of molecules that are organized by memes, and then that forms a soup, and from that functions and blah, 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 and memes emerge at a higher order of magnitude, and they drive the system. And if it's just turtles all the way down. Okay, well, what is this? Okay, it's all about atoms. No, it's not. It's about quantum mechanics, and so we can go from galaxies down to quantum mechanics, and at every layer of scale, you'll just have stuff. And if you look at the stuff closely, it's just little bits of stuff at a lower that are organized by memes, and you get this kind of infinite regress. It's an interesting perspective. I'm not sure if it works, but it's kind of interesting, I think. Yeah, so that's one thing I'm trying to think about is, can you do, this is where I go back to category theory, because in category theory, you collapse and clustering. So there's this concept in category theory called a cone. And basically, it just means that if you have some function graph that has a single input and a single output, you can represent that, or it is essentially identical to a single thing that takes a lower order an input and output. So if you take a computer function, you've got a whole bunch of source code inside the function, but you can collapse it up to a signature, which just takes a bunch of arguments and returns something, right? So that's this idea of a cone. And then you go into that one and you go, okay, what's this statement doing? Well, it's a function too, and it has its own cone, and you can go all the way down. systems that don't replicate fade away. And so if you wait a long time, the only things that will still be around are the replicators or their outputs. So that's the strong view.
I wonder, you can probably also combine that or connect that with the stuff we're doing with Robert about like probabilistic programs, right? Like essentially they take these, there are these cones, right? You give this inputs, but you basically have no control over what comes out of them, which is a feature or a bug, depending on what you're trying to do. Like you can unleash them by just seeding them with different things and chaining them in all sorts of ways and see what happens. And you can't control it, you can't understand it, but maybe new things will emerge from it, I guess. And that orchestration, I guess, is the name of the game. Like how do you orchestrate a bunch of relatively simple things chained together in novel ways that you can't possibly hope to understand? Is there a systematic way of getting them to do something useful that you want?
Right, yeah, so yes. Anyway, so the key to this, and I know we're running out of time here, but the key to this, in my opinion, is this idea of building the two things. We need to build something that, once again, I don't know whether the right word is emergent or marginal probability, but a system that stuff comes out of periodically, right? There's a stochastic system that generates these things from time to time. Okay. And one of the things that this system can generate from time to time is a self-replicator. And if you, even a very primitive one. But if you can generate a self-replicator and you wait a while, all you'll have left is descendants of the replicator, because everything else would have statistically just faded away, right? Just through entropy will go away. And then all you'll have left is a bunch of replicators, because they're the only things that can survive. And so really all we have in the world is a bunch of stuff and a bunch of replicators.
Well, all live things, right? I mean, rocks aren't going to go away because they're not replicating, right? If you can't die, I guess you're not going to go away.
But the rock will go away. It'll turn into dust, right? Its structure will not be infinite.
Sure,
whereas if that
general
rock turns into a person who can build a spaceship and fly away to another planet and have kids who then build more spaceships who fly away to other planets, they're going to outlive the rock.
Maybe, but I wonder, like, I don't know if that's true or not, but I wonder if the simpler things are longer lasting, because the human being is very complex. A lot of things have to go right for the human beings to survive for 1 billion years. Whereas a rock could probably sit on Earth maybe until the sun burns out. Even then, it might fly to another planet somehow. So I wonder if there's also that complexity.
Absolutely. And this gets into, I don't know if you're interested in time crystals, these things that essentially can travel through time. You know, replication is a really good way for memes to survive for a long period of time, right? So the way for a meme to survive, and perhaps a rock isn't a meme, is to self-replicate, right? So anyway, that's where I don't have any programmatic anything to do anything with this idea. And that's why I was thinking about evolutionary programming and this idea of, so they have these trees where this node of a tree is just a bunch of functions that are linked together here. And if you go into that function, it's just a tree of a bunch of functions. You know, this is the evolutionary stuff that I've heard about through the book that you suggested, Payam. And I'm very interested in that, but I don't have even a doorway to it. I don't even know where to begin. So perhaps I should dig into that, because it sounds like they've done a lot of very interesting work on this area. Yeah,
I think John Holland is another person you might want to look up. Their work is on genetic algorithms. Like he came up with the whole idea, and he has lots of really good books and articles and stuff.
John Holland, let me write it down.
Another friend of Doug.
Oh, really?
Personal friend? Oh, wow, cool.
Yeah, he was at Michigan. My brother was there.
Oh,
wow.
okay.
Okay.
Nice.
Gosh. Well, we might have to get him to come and visit us through Doug. But
is John Holland alive?
Yeah, I'm not sure he is.
Yeah, I think
Okay,
he
it's
might
an
have
old-
passed away a few
it's
years
in the
ago.
previous
Yeah, the
generation.
visit would be even more interesting.
Yeah, I have his book actually right here. It's called Emergence. John Holland.
Okay,
So it's a little bit dated. It's so there is, yeah, so there is lots of stuff happened since, but it's still pretty good.
let's see if I can get it on Audible.
Yeah, one other thought, if I kind of mentally rewind the last sort of 10 minutes here, it kind of strikes me that Facebook has probably been doing this for some time. And what we will confront is a world in which someone has already sort of gone forth and terraformed the land. And then we have to deal with that.
Yes, yes.
But I mean, maybe I'll give you like an opposite perspective, like maybe just from a personal perspective, like almost everything that replicates uncontrollably, like a meme in social media or a kind of work that people do that gets super popular, like I just personally get uninterested in it. I would like things that don't scale, that are special, that are maybe need a lot of work to maintain and create. So maybe that's just a personal bias, but I feel like there is a lot of room, like maybe just because everything is super connected now these days through internet and social media, we get to see the things that did replicate, but we forget, we don't see the things that don't replicate. And those are the things that matter the most, I think. And maybe eventually they will replicate in under the right circumstances. But for me, those are the more interesting stuff. Like what almost like I get bored with whatever is like popular, like I just turn those things off because usually it's ultimately pointless. I mean, I don't know. It's the same with movies too. Like a movie that everybody likes is, I think by definition, garbage. Like I don't think you can create a movie that everybody likes. So if you create a movie that some people really like and some people really hate, that's the kind of movie I want to watch. But that kind of movie maybe doesn't replicate as well. I don't know.
Yeah, I don't have any mathematical tools, and that's what I was trying to get at later in the document. If you ever look further down, I was trying to do some of the math to build up. I don't have any kind of.
I mean, the problem is there is a selection bias, right? I mean, you only get exposed to things that replicate it, right? And so
Yes,
then
yes,
among
yes.
those, maybe you pick the ones you like and you feel good that you're like finding great things, but there's lots of great things out there that are really hard to find. So that's why I kind of like evolutionary approaches, because they rely on randomness. They don't rely on just the fitness. I think the randomness is a key ingredient that you need to explore things that you should not be exploring if you look at the numbers or the current state of things. And if you don't do that, you're gonna, if you just follow the whatever is the best or the most popular, you're not gonna go somewhere good.
Fascinating insight. Very cool.
Well, it's just like being back in high school.
Yeah, yeah.
All right, guys. Well, we're at time. Very good conversation as always. Thank you for the books, Payam. Great conversation. Any topics for next time? I think I'm going to try and angle into this evolutionary genetic algorithm stuff. So I might look at some of the John Holland stuff. Is that relevant to you, Payam? Are you interested in that?
Yeah, totally. I don't know enough about it and I would love to learn more. Even if you want to do something hands-on, like I think they're pretty, like to create simple things is actually pretty easy. Like one of the attractions of evolutionary algorithms that there's really simple to create a program. You might not get anything out of it, but it's not that hard.
Well, the beauty of that is that if we can create very simple programs, I can code them as shaders in GPU land. And so we could have, we could use thousands of concurrent experiments on the GPU, because GPUs these days are full-on computers, like they're Turing machines, basically. So very, very interesting. All right, great. Well, it sounds like we've got a thread to move along. So that's wonderful. Well, thank you both. And if you're going to do a visit to Simon Fraser, let me know, and I'd love to tag along if that's okay with you. I'm already collaborating with them. I'm doing the SIGGRAPH thing with profs from Simon Fraser. Very positive relationship. I have patents with them. So yeah, very cool.
Awesome. Sounds good. Just one note, I might not make it next week. I have an appointment at 8:30 a.m. I don't know if it'll finish by 9:30. So if it does finish, I'll be here. Otherwise, I'll probably skip next week.
That's fine, and these meetings are going to get skippy too, because I'm going to miss some of them as well. So let's just, you know, just whether the like Rose couldn't make it today. I think this is going to be the state until we get back into the fall. So
sounds good. Well, I mean,
No
if I
problem.
don't see you, happy Canada Day and happy 4th of July, I guess.
Yeah,
and,
absolutely.
We'll take it in a couple.
Yep.
Excellent.
All right. Thanks, guys.
Thanks,
Thank
guys.
you.
All right,
Take care.
take care. Peace. Bye.